CR 390, group number 10.
I am Brittany Dale.
My name is Siobhan Watkins,
Jamie Lee.
and I will begin by showing the non-inverting circuit. We use a 1 and 2 kilo ohm resistor as well as the operational amplifier. As you can see by looking at the first circuit, we have our input hooked up to our oscilloscope and our output hooked up. We also have at the top of the board our negative and positive 12 volts that we are putting in to our amplifier, and on this side we have our ground. I will now show you the results for the output to the oscilloscope. Channel 1 and channel 2, both of them are supposed to be similar. This is channel 1 and this is channel 2. And we mesh both of them together. We are putting in for this circuit 10 kilohertz, and we are using 1 volt peak to peak.
Okay, the second circuit that we built is the summon amplifier. What we have here is 3 resistors in parallel and 1 in series. Each resistor is 1 kilo ohms. Frequency we have in is going in is 10 kilohertz, 1 volt peak to peak. A summing amplifier combines different signals, voltages going in. It can either add them directly or scale them down to some combination rule. A summing amplifier with different resistors on its inputs gives a weighted sum. This can be used to convert a binary number to a voltage in a digital to analog converter. On the oscilloscope, we have our input and output, channel 1 and 2. As you can see, this is channel 1, our input, and channel 2, our output. Our waves are basically the same for input and output, a sine wave. But on here, as mentioned in our lab, we're getting some type of error. All our sine waves look like rectangle waves and square waves. The summing amplifier.
Hello. Up next is our integrated op amp, which performs mathematical functions of integration. On our circuit board, you can see here, we have 1 kilo ohm, which is in series with a 2.2 nanofarad capacitor, which is in parallel with a 100 kilo ohm resistor. The magnitude of its output is determined by the length of time a voltage is present at its input. The output voltage is proportional to the length of time a voltage is present, and the longer the input is present, the greater the output becomes. This is a picture of, this is our output on the oscilloscope. These are actually squared, and then we had the triangle output, the input.
So basically it took the integration of our square wave input and gave us the output of a triangle wave.
The next circuit that we'll be showing you is our differentiator circuit. The differentiator circuit is the exact opposite of the integrator circuit that we just showed you last. The differentiator circuit performs the mathematic operation of differentiation. As the integrator circuit, we have a resistor and a capacitor which form an RC network across the operational amplifier, and the reactance of the capacitor plays a major role in the performance of the differentiator amplifier. When we put in a square wave, we produce a spike output, and we'll show you now on the oscilloscope. You see it? Move it up and down. Up and down. Yeah. That is our input,
A square wave.
and our output, a spike.
Okay, last but not least is our last circuit, the comparator operation amplifier. And basically, what this op amp does, it compares one voltage going into another voltage going in. There are several ways that the 741 operational amplifier works. It depends on how the components are connected to the op amp. When there are no components connected to the op amp as our circuit, it operates as a comparator. Any difference between the voltages, even if it's small, drives the op amp into saturation. When the voltages supplied to both inputs are of the same magnitude and same polarity, the op amp output is 0. And as you can see on the oscilloscope, for both our inputs, we have a positive 12 going in the sine wave. So you can see that we have a sine wave as our input and 0 volts as our output. And this is EEGR 390
310
Module 2 operational amplifiers.